Hello. Welcome to the Wjec Chemistry D block, Unit 3.4. Today we're going to be covering the whole specification which is needed for Wjec, and we're going to go straight into it with the definition of a transition metal. And this is an element that possesses a partially filled D subshell in either its atom state or its elemental state, you could say, or in a stable ion. So an example of this I've got written down here. Magnesium. Now, magnesium has an atomic number 25, so this is how you write out in its element state its configuration. So we've got 4s2, 3d5. And now I've wrote out one of its stable ions underneath, magnesium 2 plus. Now, as you can see, both of these are transition metals or transition ions, because this has partially filled D subshell, and so does this. Now, it's careful to note that when you ionize a D block element, you lose this 4s2 first. And that's because if you remember from AS, this 4s subshell has a lower energy, slightly lower energy than your D subshell. Okay, so now when I said before they have this oxidation states, one of the components of a transition metal or characteristic is variable oxidation state. So an example of this is magnesium. So magnesium, we have a +2 oxidation state, a +4 oxidation state, and a +7 oxidation state. Now, usually when you see these higher oxidation states up here, you'll see them bonded to a very electronegative element. So for Mn+7, you'll know it from potassium manganate, or MnO4-. Usually you have the K in front of it, but the ion is MnO4-. Magnesium has a +7 oxidation state in this. For magnesium +4, you have MnO2, which is like a black solid. It's kind of, you might get it as a byproduct of some reactions or of an oxidation reaction. But with Mn+2, you will just see that in solution as Mn+2 ions. So because it's a low oxidation state, it doesn't need to be bonded to this electronegative element that is oxygen. Okay, so now another point of call is two elements that are in D block but aren't a transition metal. So these are cadmium and zinc. No, not cadmium, sorry. Scandium. Where have I got cadmium from? I was thinking I've got a cadmium badge right next to on my desk, so that's where I got cadmium from. So scandium and zinc. And this is because both of these only form stable ions as that do not have a partially filled D subshell. So zinc, in its normal state, has a full D orbital. And even in its +2 state, because that's the only stable ion it forms, 2 plus ion, zinc 2 plus ion still has a fully filled D subshell. So the way we could write this is we have 4s2, 3d10. So even if it loses these 4s2 electrons, we still have this full 3d10 subshell. Now with scandium, we have the same sort of thing happening. So we have our argon core, and then we have 4s2, 3d1. So we have a partially filled D subshell as it's in its elemental state. But when we have it in terms of an ionic state, the only stable ion scandium will form is scandium 3 plus in oxidation state. 3 plus ion. And this is just our argon core. We don't have any 4s, no 3d, because we've lost our 4s, and of course we lost our 3d. So that, as an ion, doesn't show our colour, or it isn't a transition metal as such. This is actually a D block element. Now, a D block element definition, remember, is just an element which has outermost electrons in a D block subshell. Okay. All right. So now we've seen up here that manganese has different oxidation states. Now, the reason for this is that transition metals can have different oxidation states because the energies of the 4s and 3d orbitals are very similar. So the ionization energies, therefore, are also similar. So that's the reason why we've got this very small difference in energy between the 4s and the 3d. Okay, so now we're going to move on to more on transition metals, which is complexes. So from a transition metal complex is where a central metal ion is surrounded by ligands Now, ligand is also another word. Ligand is a small molecule or ion with a lone pair which can coordinately bond onto a transition metal ion. Now, there are two forms that you need to know about. We have monodente, mono meaning one, and bidente ligands. So we have monodente ligands and bidente ligands. Now, the definition of a monodente ligand is where it has only one atom which can bond to the metal ion. Now, we'll see how they bond in a minute. So, of course, bidente, bi meaning two, is a ligand with two atoms which can form coordinate bonds to the metal ion. So that's the bonds they form, coordinate bonds. So they must have lone pairs. So an example of a monodente ion is water. So if I draw out water like so, we have this bent shape of a 105.5 degree bond angle, and we have two lone pairs on the oxygen. So that is an example of a monodente. There's only one atom which can coordinately bond onto the central metal ion. Now remember, a coordinate bond is when both electrons come from one atom. So in this case, if we had, for example, Al, we know that has a empty orbital. It can coordinately bond onto that. Now, aluminium isn't a D-block element, but it's the first thing that sprung to mind. Okay. Now, an example of a bidente ligand is the ethanoate ion, C2O4. Now, this is like so. There are only two atoms which can coordinately bond onto the central metal ion via coordinate bonds. So yeah, like so. Okay, so the complexes these can form, for example, are octahedral complexes, which, as you remember from AS, has a 90-degree bond angle, or a tetrahedral complex, which, as you from AS as well, is a 109.5-degree bond angle. Now, a little recap on how to draw these is this. So for an octahedral complex, you draw it like so. I'm using A and B as our ligands just to show this one. This is the dashed and wedged structure. So this will be octahedral with our 90-degree bond angle in between. And our tetrahedral is like this. I've always been told to scribble then. Dashed and wedged, you generally colour in the wedged. You probably wouldn't lose marks for it, but it's more of a etiquette kind of thing. So this tetrahedral, as you remember, has a 109.5-degree bond angle. Okay, so this is the shape of the complexes. Now these are dependent on three things: the metal's oxidation state, and the ligands themselves. So ligands can alter the shape of the complex, the oxidation state of the metal can, and the ligand. And the metal, of course, because I think I said ligand twice. So if we have, let's say, an octahedral, and we want to go to a tetrahedron. Now this is called a ligand exchange reaction because we're changing the ligand, which will therefore change the shape. Oh. So an example of this is cobalt. So I'll use cobalt chemistry. So cobalt, we have hexa aqua cobalt, like so. Now this is our octahedral, so I'll write oct. And now if I add 4 chloride ions, we're actually going to go to a tetrahedral shape. Now this tetrahedral shape is going to be down to this, COCl4, 2 minus. Now from naming it, now I can say, as we can see here, this was hexa aqua cobalt, but with this one, we're going to have tetracobaltate 2. Because as it's negative the charge, the name changes to the Latin name. So cobaltate cobaltate 2 from cobalt 2. Now usually you add 8, but in some cases where you have to slightly change the name. So iron, for example, would be ferrate. Okay. So a reason for this change in coordination number. Now from coordination number from AS, we looked at sodium chloride and cesium chloride. And we can say that sodium chloride is 6,6 and 8,8. But it's a bit different with D block, how we look at this. So in terms of D block, our coordination number is determined by the amount of coordinate bonds made to that central metal ion. So a reason for this, of why we can only fit 4 around the cobalt of chlorine, but we can fit 6 aqua molecules around cobalt, is because the chloride ion is simply bigger than the H2O, so less can fit around this metal ion. There's no hard explanation for that. It's simply chlorine is a much bigger molecule. Its atomic radii is a lot larger than a H2O molecule. So that's the reason for it. Now, if we look at maybe hexa-aqua cobalt or hexa-aqua copper, there's a general question they can ask, and this is, why do these transition metals appear coloured? Now, I'm going to use copper 2 plus as an example. So in copper 2 plus, in the ion, the energies of the 5 3d orbitals are equal. Now, the octahedral arrangement of the hexa-aqua copper 2 plus means the energies of the 5 3d orbitals are split into 2, with 3d orbitals as the lower energy and 2d orbitals at a higher energy. So like so. So I have 3d and 2d. Now this splitting is down to the ligand. When it comes closer to the central metal ion, it splits the d orbitals up. Now, from this, we had our hydrogen spectrum answer from AS. So we have the excitation of electrons from a lower energy to a higher energy, and in the terms of hydrogen spectrum, not in terms of this, we had it falling back down through Balmer, which is the visible spectrum, which we could see. Now we have to explain this in a bit higher detail at A level. So the electrons absorb energy from visible light, or photons, and this makes the electrons excited, so they jump from a lower energy level to a higher energy level. And this is what gives the colour. Now the colour seen is due to non-absorbed frequencies, or even you could say complementary colours. So for example, if we absorb a blue light, we give off the complementary colour, which is red light. So we'd absorb blue but reflect red, and we'd see the complex as red. So in this case, with cobalt, with hexa-aqua cobalt, this is pink, but with hexa-aqua copper, we actually get that pale blue colour. And that is the reason why. Now, another question they could ask if it was in terms of copper chemistry was, why doesn't copper 1 plus show any colour? Now that's simply down to all 3d orbitals are full. There is no partially filled d subshells. This allows no electrons to move between the energy levels. Okay. So that is that. Now, another point to note is when we're talking about these movement of electrons from lower to energy levels is the kind of questions they can ask. Now, from AS, there were 2 equations you need to remember. E equals hf and C equals f lambda. C being the speed of light, h being Planck's constant, E being energy, f equaling frequency, and lambda equaling wavelength. Now, there are some equations you need to remember, as they could ask some questions on that, maybe work out the energy from what frequency given, or your given frequency lambda, etc. Okay, so now another point of call of our D blocks is their use as catalysts, so they're used in catalysis. Now there are 4 that you should be aware of, and that's iron in the Haber process, now that from AS or GCSE in fact, is the process of making ammonia from H2 and nitrogen. Now, of course, they're quite inert in themselves, so they need a catalyst to get the reaction going. So another one from our AS Unit 2 would have been nickel in the hydrogenation reaction to make margarine from saturated fats. So nickel from hydrogenation reaction. And then you've also got vanadium 5 oxide. So vanadium 5 oxide. This is used in the contact process. And then the last one is magnesium 4 oxide. and this is used in the catalytic decomposition of hydrogen peroxide. So therefore you should be aware of. Now you should be aware of the two types of catalysts. So we have a homogeneous catalyst, which is when it's in the same physical state as reactants, and the heterogeneous catalyst, which is when it's in a different state to reactants. So homo meaning same, hetero meaning different. Okay, so for homogeneous catalysts, you need to know how they work, and so do you do with hetero. So for homogeneous catalysts, their uses are due to their variable oxidation states. Now, this is to reduce and oxidize a reactant, making it more reactive. And of course, the transition metal can go back to the original oxidation state by reaction with another molecule, hence why it's a catalyst. As you know, catalysts are always reformed at the end of a reaction. Now, a heterogeneous catalyst kind of works in a different way. Now, because it's in a different state, it can't switch its oxidation state as easily. So it works by having partially filled D subshells. Now, the catalyst provides a solid surface for which another reaction or alternate reactions can take place, which you can get to the same end product. So the catalyst provides a solid surface on which reactants can adsorb. So adsorb, not absorb, so adsorb onto the plane, bringing them closer to react with each other. So if they were to all adsorb onto this, you can see it brings them closer. Now this is a bit like in enzymes or in biology, for example. You know that some of them adsorb onto an inner matrix in order for them to work. Now, molecules with lone pairs from this can form coordinate bonds also with the metal atom. Now, this is due to the d orbitals to bond to. So that's another way of heterogeneous catalysts can work, down to them having available d subshells on which lone pairs can coordinately bond onto. Okay, so the final thing that I've saved till last is the colours of complexes that you need to know, and the different oxidation states also. So some you may already know from AS and from your organic, and some you may not. Okay, so the one we're going to start off with is dichromate, which is like so. So this is chromium in oxidation state +6, and this has an orange colour, so as you'll know from your oxidation reactions. And of course, the next one you need to know is chromium 3+, which you also know from your oxidation reactions, and this is green. Another one you need to know is CrO4 2-. This is when it's in oxidation state +6, and this is yellow in colour. Okay, so now you need to know MnO4-, which I may have mentioned earlier, is purple. You need to know that the cobalt 2+ ion is pink. You need to know both of the ions. So we have iron 2+ and iron 3+. Iron 2+ is this pale greeny colour, and iron 3+ is brown, so like a rusty brown colour. And our copper 2+ is pale blue. Sort of the colour you'd see with the copper sulfate solution you'd see lying around the chemistry desks in school. Okay, so they're the colours you need to know. Now what else you need to know is also some of the reactions with hydroxyl ion. So there are 4 key reactions you need to know with the hydroxyl ion. This is chromium, iron, both ions, and copper. You also need to know about which ones are amphoteric. So I'll make it easy. Only one of them are amphoteric, and that is chromium. Chromium is the only amphoteric one. That's when it can react as both an acid and an alkali. Okay, so I'll start off with chromium. You also need to know the colour changes for these. So we have Cr3 plus 3OH minus, and this is going to form a precipitate of chromium, like so. And this is greeny grey colour, greeny grey solid. And then, as it's amphoteric, it can react once again with further OH minus. So CrOH3 plus 3OH minus is going to give CrOH6 3 minus, and this is a green solution, also known as hexahydroxychromium chromate 3, because it's got that minus charge, remember, so it has that chromate name. Okay, so that's the chromium one. Now next to iron 2. So iron 2 plus 2OH minus is going to give FeOH2. Now this is a dark green precipitate. Dark green precipitate. Now PPT for reference means precipitate if I write it down. You also need to know the iron 3 plus. Now this is going to go to FeOH3, which is also a dark browny colour. Now it's also good to note that Fe3 plus, as said before, is a brown colour. But if you have it in water, it can also be a slightly yellowy colour, so browny yellow, because they might mix that in. And of course, the last one you need to know is copper 2 plus 2OH minus is going to give a blue precipitate of copper hydroxide. Copper 2 hydroxide. This will also be blue. Okay. Now they're the simple ions, colours that you need to know in the reaction with OH minus, but there are also some complex colours that you need to know the name of, as well as the name of the colour. Okay, so hexa aqua copper 2. Don't forget the 2 in the naming of it. I always forgot to do that. So what I mean by that is it's going to be hexa aqua copper 2, like so. Okay, so the next one you need to know about, so that's the copper one, and of course, did I say the colour, sorry? Oh, sorry, I didn't say the colour. That is going to be a blue. So like the copper sulfate kind of blue that you'd see in the lab. Zoom us back in. Okay, so the next one you need to know about is hexa aqua cobalt. Cobalt 2, keep forgetting about that. And that's pinky colour, a nice kind of pinky red. The next one you need to know about is another copper chemistry one, which is CuNH3. So it's going to have a slightly different naming because of the NH3, H2O. So it's still going to be 2 plus because ammonia carries a neutral charge as well as water, as you know. So this is going to be called tetraamine diaqua copper 2. Now, when I say amine, it's not the same as amine from Unit 4, so it's going to be tetraamine diaqua copper 2. So that's how you say it. It's got a double M, tetraamine. Okay, so now we're going to do iron 3, so Fe. This was on about before when I said about the yellowy colour. You could describe tetra aqua iron 3 as a yellowy colour. Yellowy-ish brown. It's not the technical term, but it's the name of it. So yeah, that's hexa aqua iron 3. So now there are 2 tetrahedral complexes you need to know about. So they are octahedral. We're going to have CuCl4 2 minus. So this is tetrachlorocuprate 2. And then you need to know about the cobalt version of that too. So tetrachlorocobaltate 2. And that's a blue colour. And here, sorry, copper tetrachlorocuprate is a yellow colour too. Okay, so I hope this video has been helpful. Well, have I missed anything? Oh, okay. I'll go on quickly on to say this. So they could throw in a sneaky question on maybe the biological importance of some transition metals. Now, it's not directly incorporated in the course, but they have been known to throw in some cheeky ones like this. So titanium can be used in biological molecules. Iron, which iron is known, if you do biology or just in general knowledge, is a constituent of hemoglobin. And that's what carries oxygen around the body. Titanium doesn't actually react with bodily fluids. It's not toxic as well, and it bonds to bone. And a little fact apart from this is titanium was actually discovered as prosthetic by a scientist who was putting a titanium window to see inside of a rabbit while performing surgery, and you could see that cells were starting to form around this titanium, and that's where we get the modern day prosthetics from. So for titanium, I'll put prosthetics. And the final one is cobalt. You just need to know a couple examples. It's not a major thing, but we'll go cobalt, which is actually a vitamin B12 constituent. So that's about keeping you awake. Okay. I suppose you also could say zinc is part of enzymes. So enzymes for DNA or RNA. So RNA just DNA enzymes. And that's really all you need to know about that. Not too much detail, but I'd have them in the back of your mind in the exam. So I hope that's been helpful. And if you want to check out my TikTok, I've also done a little video on the copper chemistry of D-block elements. My TikTok is also WJC A level help. And I try and do small little videos to help with revision. So I hope that's been useful. Thank you for watching.